Hi everyone. Our topic for today is processing of nanomaterials. I am Hussaini and she is Beg. Everyone in this class, I guess, and I hope that is aware of the nanoscale range, which is 1 nanometer to 100 nanometers. However, I am going to talk about the processing of nanomaterials, and it has two approaches: the top-down approach and the bottom-down and the bottom-up approach. The top-down approach is you take a larger material and you break it down into smaller ones. So it's like you flow from high to low. The bottom-up approach is just the opposite of that. You take the smaller materials, you start from atoms, molecules, and you combine them to give you the bigger material of our interest, which is the nanomaterial. There are a variety of techniques available for that. A few of them are lithography. We have AFM, STM for nanomanipulation. A variety of techniques in lithography is photolithography, electron beam, and X-ray. The difference between them is the source of light. I'll talk about the top-down approach, and as I said, it's like you build a material by taking a large size material and breaking it down. A very typical example for that is mechanical accretion or milling. In layman word, it's grinding. And I have a small video for you. There are two approaches to the synthesis and processing of nanomaterials: A, top-down, and B, bottoms-up. I'll demonstrate to you the top-down approach. As the name says, top-down method involves taking a chunk of material and breaking it down into smaller size material. Milling is a typical top-down method. The biggest problem with top-down approach, as you have seen in the video, is the imperfection of surface structure. Such imperfections would have a significant impact on physical properties and surface chemistry. I'll talk about the advantages and disadvantages. The top-down approach is a very versatile one. As you can see that you can take a part and just pattern and build it in the same place. So the additional step of assembling the different parts is avoided. A very good example is electronic circuits. Consider your computer motherboards. So it's just you take a part, you build a part, you pattern it, and build it at the same place. You do not have to merge all the small parts for your motherboard. The biggest disadvantage with this approach is the surface imperfections and the surface imperfections. This leads to has a adverse effect on the physical properties and the surface chemistry of your nanomaterial.
Okay, it's my turn to talk about the bottom-up approach. First, let's see the definition. As we know, the biggest difference between the bottom-up approach and the top-down approach is that the bottom-up approach is started with the single atoms, molecules, or the clusters, and bring them together to groups. And finally, we can build the materials up from the bottom. If you are still confused about the definition, doesn't matter. We have a video made by our yeah.
Hi everyone, I'm going to talk about bottom-up approach. The biggest difference between top-down and the bottom-up approach is that the bottom-up approach is started with the individual atoms, molecules, and the clusters. Then they will come together like this. To form the products in which every atom is in a precise designed location. So finally we can get the nanomaterials we designed. Unlike the top-down approach, the bottom-up approach also promises the better chance to obtain the nanostructures with less defects, more homogeneous chemical composition, and a better short and long-range ordering.
Okay, I hope from our review you can get a better understanding about the bottom-up approach. Let's see some two examples. First one in the polymer sense. As we know, the polymers are synthesized by the connecting individual monomers. From this figure, we can see the monomers connect together to form the long-chain polymers. And also in the crystal growth, the growth species like the atoms, molecules, or clusters, they will assemble into the crystal structure one after another on the surface. So finally, we can get the crystal materials we want. And let's see some, because there are many different methods about the bottom-up approach to make the nanomaterials. So let's see some examples. The first one is the most typical example of bottom-up approach to make the nanomaterials, the homogeneous and heterogeneous nucleation. This figure clearly shows us the two species are maybe the single molecules, atoms, or the clusters. When they come together, they will have the nucleation, and the left two is the heterogeneous nucleation on the substrate of the on the interface between two phases, and the right one is the left one is heterogeneous, and the right one is homogeneous nucleation on the liquid phase. And there are other some examples about bottom-up approach, like the chemical reactions in small space and the depositions. Because my teammate have already introduced the advantages and disadvantages about top-down approach, so we will also talk about that, about the bottom-up approach to make the comparison. Let's see the advantages. First one is the bottom-up approach is cheaper and is easier than the top-down approach. And the second one is, since we know the top-down approach needs the external stress to make the nanomaterials, so the biggest problem my teammates have already introduced is the defects, impurities. However, the bottom-up approach is mainly driven by the reduction of Gibbs free energy. So the materials is in a state which is closer to the thermodynamic equilibrium state. So the advantages of bottom-up approach is to obtain the nanostructures with less defects, more homogeneous chemical compositions. However, bottom-up approach still has some disadvantages, which is be overwhelmed as the size and the complexity of the design assembly increase. However, we still can make a conclusion that the bottom-up approach plays a very important role in the processing of nanomaterials. Okay, so my teammate will talk more about the lithography, so it's his turn.
I'll introduce to you lithography. The first technique I'll go through is the photolithography. I'll divide that word into three parts: photo, which is light; litho, which is Greek for stone; and graphic, which is writing. There is a small representation here. As you can see, first we have to coat the base material with the resist, which is a polymer, and then you insert a mask and expose it to light. Depending on whether your resist material is sensitive or insensitive, I'll start again. You take a base material and coat it with a resist material, which is the polymer, and you insert a mask, and then you expose light to this material. Depending on whether your resist is sensitive or insensitive to light, you get a positive or a negative. Then you take this material and develop it and add some etching agents which will etch down your base material, thereby giving you the final nano product. I have a small demonstration on photolithography.
Facility, where we make a lot of nanoscale devices. The nanoscale is very small. It's about the size of about a nano. Daniel Woody, and I'm an engineer here at the Cornell Nanoscale facility, where we make a lot of nanoscale devices. The nanoscale is very small. It's about the size of about a nanometer, or hundreds of nanometers at most. That's an exciting place to be. Not something you can never see with your own eyes. It's so small that you really can't see it. Photolithography. Photolithography is actually where we print with light. That's what photolithography means. Photo meaning light, and lithography meaning to print. So photolithography is printing with light. So every time you take a picture with your camera, and to some extent you're doing photolithography. It's a little bit different than what we do here. This is a mask we use for testing the tools. It's got lines that range from 100 microns, or about the size of a human hair, down to about 1 micron, or 1,000 nanometers. We shine the light through the mask, and either the photoresist is exposed or it's not exposed. Instead of it being, it's either got light or it has no light. So again, that's why it's black and white with only two colors. Either exposed by light or not exposed by light. And then we're able to take the pattern that's on our photo mask and have it appear on our substrate, and then we can use that to help build our nano device. Okay, I'm loading the photo mask into the tool. And it's going to pick the photo mask up. That will then allow me to load my wafer in. Once I load the wafer in, I'll use these controls to move the wafer around underneath the mask to make any previous pattern on the wafer line up with the pattern on the mask. So now my wafer's been exposed, and we can go and develop it. It's sort of like developing film, and the image we just shot in the wafer will appear in the photoresist. Photolithography, or printing with light.
Okay, finally let's make a conclusion. I know you cannot digest everything we presented today. Doesn't matter. If you forgot almost the thing, doesn't matter. The only thing we hope you can remember and understand from our presentation is the basic idea about top-down and bottom-up approach. This figure clearly shows us the top-down approach is from the bulk of materials to the nanoparticle or nanomaterials. And the bottom up is from the atoms, molecules, or clusters to the nanoparticles. So thank you for your attention. Any questions?